Thank you very much for the introduction. Some of this talk comes from previous ones of our webinars, and since I moved back to Australia, I've made them more relevant to the local environment. And this one, we're going to talk particularly about some things concerning wind engineering in Northern Australia and Darwin in particular. Because of the educational nature of what we're talking about, I just want to give some generic credit or specific credit to a variety of organisations that I've basically taken slides and videos from. So there's very well-known wind engineering universities up the top. In Australia, obviously, Monash University, Hong Kong University of Science and Technology, and some consulting firms also contributed. So rather than me saying this is from Joe Blogs all the time, I just want to get that out of the way up the front. Okay, wind engineering, when you're designing a building, and my focus in this talk is going to be tending to be tall buildings, and a lot of it applies to shorter buildings as well, but that's my focus is going to be taller buildings. And I've noticed that there's been a change since I was last in Darwin. You've got some reasonably large buildings appearing on the horizon in the downtown. I think there's been a change in height limits possibly. But I think I saw something looked like it was about 30 or 32 stories. So that may be a part of the future, and there's plenty of cities that are in cyclonic areas and hurricane areas or typhoon areas that have tall buildings in them. So it's not something that we should be frightened of, we just have to design it correctly. Refer you to places like Miami and Hong Kong and Taipei and these sorts of cities where there's tall buildings. Here in Australia, we can assess the loads on a tall building. I'm going to look at just really two principal areas, cladding pressures and structural loads and dynamics. There are two methods, and obviously there's the code, which you're both familiar with, AWES 1170, and it's actually created from quite a few, let's set a little timer off here, give me a chance. It's actually based on literally hundreds of wind tunnel tests in a sense. So when you're doing a site-specific, building-specific wind tunnel study, which is what we'll be talking about here, you actually get something that's more pertinent to your given structure because all the surroundings are being modelled as appropriate. And when you do that, the wind tunnel test actually supersedes the code in terms of loads if you're the structural engineer. Briefly, what sort of windstorms are we dealing about? There's four listed here. I suggest that the focus for us to talk about in Darwin is the centre two, tropical cyclones, also known as hurricanes and typhoons, depending on what part of the world you're in. They are heat-driven. They exist typically between 5 and 40 degrees latitude. They're on the oceans. When they go over land, they tend to lose energy, both through friction and the lack of heat coming in to drive them. If your water temperature is less than about 26 degrees centigrade, you're just not going to get a hurricane or a cyclone. And then the other one that's pertinent to Darwin is the classic wet seasons. I've been up here when you've got thunderstorms you can almost set your clock to coming in the afternoon. Those will cause downbursts, and I'll touch on those briefly as well. This is actually taken from insurance background I got from a German insurance company, and it's got lots of natural disasters on it, but let's just focus on the green areas. That's where cyclones and hurricanes occur. Two things you might notice: the equatorial region has none because there's no Coriolis force. The cyclone, hurricane can't turn and be created in the first place. And also the thing that really struck me when I saw this was South America. It's got cold water going out both sides, and so they tend not to have hurricanes. Moving on to thunderstorms, this is a bit of information I took from the Met Bureau. We had a downburst in Brisbane at Archfield Airport, and we caught the information here. And I went onto their website and I took the data and put it on this little spreadsheet. But really what I wanted to focus on is just one particular thing. This is a reasonably damaging downburst. What happens to thunderstorm, you end up with moist air rising, eventually it gets to the point where it condenses and cools, you get a cold and a cold air that just comes out, you'll experience that, and it rolls off almost like a rolling donut on the ground, is what the air is doing. And here I can't read that, but from 422 to 430 in a period of 8 minutes, it went from 40 kilometre an hour wind speeds at the airport to 140 kilometres an hour in an 8 minute period. The reason I mention that is that in your city, when you're dealing with the ultimate limit state design, you're concerned about cyclones, you're actually in quite a good condition because you've got sufficient time to lock up your building, office building or residential building, run around, close the windows and that sort of thing. For the serviceability type event of a thunderstorm, you're unlikely to be able to get around the building in 8 minutes and close it all up. The wind speeds aren't as much, but they can do damage. And I've got plenty of examples I can talk to you about afterwards when having a drink of how that happens. This other plot down the bottom, which was the temperature, I thought that was interesting. 15 degrees temperature drop in that same 8 minute period. So those are the two types of windstorms I want to focus on. In the wind tunnel, we model them as an atmospheric boundary layer. This is a classic drawing here. Basically what I want you to get out of it is that depending on the surface roughness here, in Australia we have terrain categories 1 through to 4, although I don't think 4 is used anymore. So with increasing friction, this part of the atmosphere called the boundary layer is influenced by the friction in the ground. So nominally the mean velocity beyond those heights in those examples is relatively constant with height. So it's just the part of the atmosphere that we live in, the bottom few hundred metres, where friction on the ground causes this mean profile with a curvature in it. And that's what we model in the wind tunnel. A little sketch up the top sort of illustrates that superimposed upon that, the real wind is gusty. And so it's gusting back and forth. We've got this little attempt to sketch that at the top there. We've got to model that gustiness correctly, the energy content and the spectra of those gusts in the wind tunnel at a scale. What does a wind tunnel look like? Generally they have a form that looks like this. This is one I worked in the United States, and it's fairly typical. It's got all the features you'd expect. It's about 20 metres long, it's about 4 metres wide. You've got trips and roughness elements up at the end, trips and spires at the end, and roughness elements in the middle distance. The wind comes towards you, turntable with a model on it. That happens to be a turntable or surface paradise, incidentally. And those are standard sort of characteristics. This is a tunnel that we just completed at MEL in Melbourne. It's actually 2 tunnels running parallel to each other. And they've both got the same features. You've got the spires at the back, the 2-dimensional trip across the tunnel, and the roughness elements. The nice feature about this one is each tunnel is 5 metres wide. If you have a project that's particularly big, like a long suspension bridge, you can slide that wall back and use the whole tunnel 10 metres wide. So it's a nice facility as a sort of new development in wind engineering. So that's what a tunnel looks like. All the ones that you deal with commissioning various projects with people who are looking general and have that sort of characteristic. Motivation for doing a wind tunnel study is listed off here. Unusual structures, a bit hard to define. I've got some examples there that I've worked on over the years. But, it could be a new telescope in the Andes, or it could be an unusual bridge arrangement in Singapore. But the point is, it's an unusual geometry. It's not a boxy building, which is what a code typically does. Could be shielding and channeling, that's sort of 2 sides of the same coin. Terrain may be important, you might want more accurate results. As an engineer, you would want that. As a developer or an architect, you might be more interested in saving money, and often that is the case. But I'd never guarantee that, because sometimes the architect comes up with an unusual design that actually makes the loads worse. But bear in mind, the vast majority of the time people save money. Also, if they're greater than 200 metres high, as a lot of buildings in Australia are now, then sort of mandatory, you have to go to the wind tunnel. Here's a couple of low-rise, unusual structures. Obviously, well-known one in Abu Dhabi, but this one here was a modest little 4,500 square metre home in California I did for a friend, and a bloke called Dwayne Hagedorn. And it's obviously is not a standard sort of building that you could use the code for. So it doesn't have to be a tall building. When I first started wind engineering, people would say, oh, it's a 20-storey building, I don't need to do it. The height was the parameter. Get that out of your mind, whatever you had in your mind. It's not that, it's the value of the building. If a building's worth more than about $25 million, you can actually do well out of doing a wind tunnel study. That's been my general feel. This building happened to be a $25 million home. Mr. Hagedorn said that's a lot of money, but when his wife starts decorating it, it's going to get really expensive. Okay, physics. We're looking at some cladding pressures here. Just a little bit of basic physics. When the wind tries to go around a sharp corner, as in that top photo, it can't stay stuck to the corner, it separates. If you're familiar with AS 1170, that's where the edge strips are, where there's substantial amount of higher pressures. And same on the edge of a roof here. And then there's some hot spots on roofs, often in the corners. And this is the roof corner board. That's the physics of why in the corner there's always higher pressure region in the code. These little counter-rotating vortices that are very effective at creating negative pressures trying to pull the roof up. You can actually do a bit to fix that by putting some fences across the roof. And I'll talk to you about that later on. You can halve your loads, but that's a whole different ballgame. Here's an interesting one here. This is the tall building, a change of the vertical line of the building. This happens to be the podium area. But, so we've got flow coming through here, a separated region, but very minuscule vortex coming up from that corner. So that's got both bits of physics going for it. The pressures on that building were substantially higher here than they were at the top of the building, which might be counterintuitive, but that's sort of how it works in the wind tunnel when you start to find out these things. You can put your money where you need it, but you don't necessarily smear it over the whole building effectively, which is where the potential for savings come in. All right, the pressure taps typically look like this. So we talked about the separation on the edge strips of the building and the vortices on the corners. That means you want more pressure taps in those areas. And in the broad faces of the model, you don't put as many pressure taps because not much happening. Okay? So you see lots of pressure taps in the corner of the model here. That's actually a building that I put in there in Palmerston, which I think is under construction. So there are projects locally that we've been looking at in the wind tunnel. You can see there's more pressure taps in the corner and edges and fewer of them in the bulk side of the building. One component of internal cladding design is also what the internal pressure is. And just to give you a feel of what we're talking about, this little cartoon sort of describes it. If you've got an open window, you can end up by increasing the net loads on the walls or the roof as a result. This is an example up the top. It was Tamiami Airport after Hurricane Andrew. You're probably familiar with the doors on hangars are notoriously porous in the Darwin airport. There's gaps all around the outside of them. The doors were closed, wind was coming in this way, positively pressurised the hangar, negative pressure over the top leading edge there, causing suction. Net 2 really just removed that edge strip pretty well as you would have predicted from the code. Okay, so that's the sort of thing that we're dealing with. A wind engineering lab will typically provide you a drawing something like this. This happens to be a building in Brisbane, where there's contour drawings of the net pressures, the internal pressure and the external measured pressures. This one happens to have a little hot spot up on the top corner there. As we finish off with the pressure side of what I want to talk about, I just want to emphasise a couple of things. There has been a trend with tall buildings in recent times where in the past they were typically nominally sealed buildings are office buildings. Nowadays most of the tall buildings that are being built around the world and around Australia are residential buildings, which means Joe Bloggs on the 78th floor can leave his window open when he goes to work. And a thunderstorm comes along and suddenly you pressurise the inside of the apartment. If you have standard partition walls, for example, between apartment A and apartment B, you can actually get pretty severe damage when it's not even an ultimate limit state event, it's an ordinary old thunderstorm. There's already been several buildings in the south in Australia that developers have to go in and rebuild the walls between apartments because they failed. Okay, so and failure is a variety of failures I can tell you about over a drink, but the point is we can look at that in the wind tunnel and give you an idea. That's sealed building results up the top with all this red stuff here. That's when you connect with internal spaces, the pressures around the corner on one side of the building, the other, or across the building from front to rear. And so be aware of that if you're getting taller buildings in their residential, that people are going to leave their windows open. There are ways around it, and there's some discussions here that I'll have to have time to talk about, unfortunately. But one of them is a snapshot window, which is a type of window that's used on several buildings in Australia, that when it gets positively pressurised, you tune it, say, to 1500 pascals or something, it will close. And that doesn't solve the problem. You've still got the negative pressure potential in another area, but it halves the issue, and it helps to keep things under control. That's probably, let's move on now to frame loads. I'm going to look at the gross structural loads. Just to make it a bit more interesting, I want to show you some really unusual skinny buildings that are appearing in the world at the moment, and some that we have here in Australia. And the whole dynamics of tall buildings has changed. What drives it is a phenomenon like this. So in this little video here, you can see the piece of paper down the bottom. The wind is sort of going along the line of those poles, and yet the poles are moving perpendicular to that flow. So it's basically this physics here. You've got a long wind response this way, but there's vortices being shed off ultimately in time, so that there's actually a load in this direction transverse to the wind. So on average, the load in this direction is zero, but at any instant in time, it's definitely non-zero. And that's what makes tall building design interesting, to be blunt. And the physics looks a bit like this. Here is a water flume, water's coming from right through to left, and you can see the vortices being shed off the cylinder. Now, it could be a square cylinder, a triangular cylinder, a long oblong. The same thing happens, just the period in which the eddies are shed off change, and a few other physics change, but the same thing occurs. You can actually fix this by putting a strake on the building, which I have got a video of that. The time is a little bit short, which you've probably seen in chimneys, or if you happen to ever be a forex drinker, you'll see that there's a picture of a chimney on a bottle and it's got a helix around it. That's the same thing, to destroy this vortex shedding. People have tried doing that with buildings as well, with some success on it. Here's a generic load base moment diagram that has come from a building. Actually, I think it was a building in Taiwan. But moment about the x-axis, and you can see that the long wind case of 180 degrees, that's basically what the code can calculate. You've got a mean value and you've got a peak value, and it's about almost 2 to 1. And then for the crosswind case, moment about the x-axis, at 90 degrees, the mean is 0 by definition, but a very non-zero sets of peaks we talked about before. And that can drive tall building design. Keep in mind that there's another plot that looks just like this for moments about the y-axis. Imagine it down here, but displaced 90 degrees. So when you're getting a long wind in the x-axis, you're getting crosswind in the y-axis, excuse me. We could talk about this sort of stuff for quite a while, but so we give you a bit of a feel for what we're talking. The multiple lines there have to do with damping choices and or frequency choices, which is coming into play as well. So we'll look at some traditional tall buildings in Australia. There's Eureka Tower, which is built, Q1 obviously, which is built. The next tallest is proposed in Australia, called the Orion Towers, may or may not happen. Those all have height to slenderness ratios, which is height to minimum width. It's reasonably typical. You know, when I first started in structural engineering, numbers like 6, 8, 10 was extreme. You know. Well, now we're getting buildings that are substantially more slender than that. See my clock going here. Good. So this is one that exists in Brisbane. That's about 12 to 1. If you actually look at it on this side, it's a lot thinner than it appears on that image there. But it's the only building in Brisbane that's got a damping system on the top, and I'll show you some pictures of that in a minute. Overseas, I had some friends at RWDI, one of my competitors, but in this small game of wind engineering, we're all friends in reality. And they sent me this and a video that I'll follow up with. This is the building that exists, it's finished. It's in New York City, you can Google it. It's a square prism. And and that is really a bad thing for vortex shedding. And it's very tall, it's 420 odd metres, aspect ratio is 15 to 1, so that's really quite out there. And when the engineers first went into it, they knew it was not going to work very well, so they did what they could aerodynamically. And you'll notice the 50 points up the building, there are open floors. So wind can go through those floors, there's nothing in there, no apartments, and the goal there is to do two things, to help decorrelate those vortices in the previous images I showed you in the video, and also to sort of decrease the base pressure on the backside of the building so it doesn't get quite negative. And then they put a damping tank in the top of it. So with nothing there, when it was just a pure prism, the goal in the United States anyway, for a tall building is you don't want the 10-year peak acceleration to be more than about 18 milli-Gs, horizontal acceleration. When they first tested it, it was more like 60, so clearly that was more like a carnival ride than a building. So then put on these holes in the building, and I'm led to believe that improved it to about 33 milli-Gs, which is getting doable. You can fix that. And then they put in a damping system which brought it down more to a level that's generally acceptable. And here's a video of the damping system working. So it's basically a giant heavy pendulum on the top of the building that moves instead of the building moving. So you think a little bit about this. The videographer standing here taking the video, he's in the building. The building's actually moving around the mass in part, okay? Not entirely, but part of it is. So it's not entirely just this mass moving in the building's swaying and the mass is going the other way. And so the end result is a building that's quite successful. Keep in mind you can afford to do these things when the low-level apartments go for $7.5 million and the upper floors go for $115 million. Unfurnished, decorator ready. Okay? So you can do it if you've got the cash and the clientele to do it. Here in Australia, we've done some very slender buildings. Here's one in Flinders Street in Melbourne. It's finished. It's called the Phoenix. It's 15 to 1 as well. It's just that it's 6 metres wide and 90 metres tall. 1 unit per apartment, of course. Originally it was going to be 20 to 1, that's the model there in the wind tunnel. Couldn't quite get that to work. But it's got a damping tank on the top, which I'll describe in a minute. There's two things that have happened that allow these skinny buildings to occur. One is, well, three things I suppose. Shortage of land with big blocks of land, so you can't go, you have to have a skinny building to start with. And a damping system on the top that allows you to actually control the accelerations, and mechanical systems for parking cars in a stacker arrangement. So you drive your car into a slot, press a button and hope it comes back when you want it. Okay? So those are the three things that allow it to happen. Here's one in Brisbane that's currently being designed in Ann Street. It's about 9 metres wide and then 42 stories high. So we're going to see a few more of these, and so I thought it might be more fun to show you them rather than standard sort of buildings, the sort of way things are going. But if architects get wind engineers involved early, then simple things like on deciding on the shape of the building, we can help. And I don't want to go too much into this, but basically this is a spectrum of different shapes and how they respond in a crosswind sense. And so the square section, like in Park Avenue, is that top curve. But if you make it an octagon, or you taper it, or you do some other things to it, you can reduce the response substantially, keeping in mind that's a log plot. Okay? So you can be an order of magnitude better by picking the right shape. That's why most of the super tall buildings in the world, the Burj Khalifas and others, all have particularly aerodynamically designed shape. And none of them have dampers, incidentally. The tallest one of the damper is Type A101, but the other ones don't. Here are some of the damping options. This is one I took a few months ago, 3 months ago, in San Francisco. It's a new building Harrison design with these huge tail advice stand. They look like a shock absorber off a four-wheel drive, but they're that round, okay? And there's 8 of them in this building, and that's one that's all covered up with protective coverings. That's one approach. This serves a dual purpose, and also it's for earthquakes as well, but it serves to keep the accelerations down to acceptable levels as well. Still going all right, okay. The old World Trade Centers had viscoelastic dampers that looked like that, thousands of them in each building. The City Court building in New York has this sort of, it's called a tuned mass damper, which is quite an efficient way of doing it. Basically, it's a great big heavy mass and moving in the building, much the same as the one that we saw in the pendulum style earlier. Incidentally, if you go to that building and ask to see it, they'll deny it exists. They're embarrassed about it. But if you push it, they'll go and show it to you. Here is a tuned liquid column damper, which basically is a giant U-tube, typically with dimensions of 8 or so metres by 3 or so metres by 3 or 4 metres high. So it's a big piece of real estate on top of the building full of water. And the natural frequency of it is tuned by the water levels inside. And that building in Brisbane has it, as does another one called the Solid. So here we have some pedestrians. So the wind is whipping around the side of this building, and all the little ducks get caught up in it, but they're obviously built for the whole problem. Humans aren't. I've got a similar video where a guy on a bicycle gets pushed off by the wind. People laugh out loud at that. The ducks are people going, oh, poor ducks. But anyway. So that's a bit of an issue with pedestrian winds. I'm not going to dwell on it, I'll just show it something that we can look at in the wind tunnel. The physics basically is something like this: tall buildings will attract wind to ground level, which in Darwin actually might be a good thing climatically. We give you more of a breeze around the base of buildings. I did a building in Singapore called Hitachi House. It's up on stilts, and that's a no-no in almost any other city in the world because it's so humid and hot there that there's a permanent flea market of the building because of this breeze that gets created. So tall buildings will tend to attract it down to ground level, unless there's lots of tall buildings like in some parts of Melbourne or New York or Houston. You don't get that issue. So be aware, we can look at that sort of stuff in the wind tunnel. I mean, there's some full-scale stuff on sunshades, and this is one of my personal beefs. There's a lot of sunshades going up on buildings. They've been designed for dynamic loads, they've been designed for mean loads. Several have fallen off buildings in the last 2 years in Sydney and Melbourne, 2 in Brisbane in the Valley 2 years ago. Nobody's been killed yet, but they will be. It's a thing called fatigue. Engineers should know about this, but they routinely ignore it when they're designing these things. And then I just flag it now. If you're in a government department or something, insist that people look at these sunshades properly. Okay, so when should you, there's some ideas of when you should talk to a wind engineer. I would encourage you to do it early in the project so we can have some input into the shape and orientation of the building. Tall and skinny, cost margin, less to do with height, but more to do with the value of the building or the complexity of the architecture. Where there might be accelerated flows or channeling and terrain coming into play. Not so much, possibly here in Darwin, we've got some cliffs along the front there, so that could come into play. And if it has a post-disaster function, which comes into it as well, design storms. And that is some references, and I think that's it. Did you want to do questions at the end?
Yeah. Any pressing questions while you're still remembering? No? Okay, questions at the end of the beer, sounds like.
Sounds good. All right then.